All right, the next thing we're going to talk about is how solids dissolve in water. We're going to look at a solubility chart that I'll give you a link for. This is going to basically describe why things dissolve the way they do and why other things don't dissolve the way they do. So we're looking at ionic compounds again, and so the ones that's going to break apart. Like I said, some dissolve more easily than others, like sodium chloride, as you know, dissolves very easily in water, but copper 1 chloride does not. So we need to figure out what's going on here. Why does sodium chloride dissolve and not copper chloride? And the answer lies in the ability of water to collide hard enough with the crystal to break the ionic bonds. There's got to be such a large collision that it's got to overcome the ability of the ions to stay connected to each other. Sometimes it's not very much energy needed, like in sodium chloride. Sometimes it's tremendous. That energy of the water attaching itself that's going to compete with that is called hydration energy. So the amount of energy for the water to hook onto something and pull it away, that's called hydration energy. The ability for the ions to stay bonded together is called lattice energy. A lattice is like a very basic geometric structure. Some people have lattice around their wooden lattices around their porch or underneath their porch. It's kind of like a very organized geometry. So if it's a really strong lattice energy, it's going to be very difficult for the water to pull that away. If the hydration energy of the water to the ions is greater than the lattice energy, then the dissolving will take place. So if the ability to latch on and pull things away is greater than the ions themselves holding together, you're going to have dissolving. If this is reversed, then dissolving will not take place. There are ways to predict which ions are more soluble and less soluble in ionic structures, but we have charts in which we look at for that, and we're going to discuss that in a later chapter, so that's not an issue. What we're going to be looking at is the ability of the ions to dissolve in water in different rates. Okay? So we're going to look at the soluble salts, not the insoluble salts, the ones like sodium chloride that will dissolve in water. And how can we get them to dissolve if they do not immediately dissolve? But we know that they will dissolve. Okay, so I have a soluble substance. I know it's soluble. It's not on the insoluble salt chart. But sometimes you put it in water and it won't dissolve real fast. So what do we do about that? Well, the best way to think about this is to imagine making Kool-Aid. So you have poured 2 cups of sugar into a pitcher, then you add a gallon of water. Does all the sugar dissolve immediately? No. Some will, but some will just sit there. So how can you make it dissolve? So what do you do in that situation when the sugar doesn't dissolve right away? Well, most people will get a giant wooden spoon and start stirring it rather vigorously. Eventually it will dissolve. But why? Why does that create the dissolving? Well, it turns out that when you stir, which is also known as agitating a mixture, you force the water and the sugar to collide more violently than if it was just sitting there when you pour it on top of each other. Eventually the sugar will dissolve, but the stirring forces collisions to occur and to occur more quickly. So agitating a solution is very important. You can shake it, you can stir it, you can do whatever it takes to get it to dissolve, but you gotta cause the motion of the 2 particles to collide with each other. So, but what's another way? That's not the only way. Well, one thing we could have done was we could have poured warm or even hot water into the pitcher instead of cold water. And of course you put it in the fridge afterwards to let it sit. So, I mean, who wants to drink hot Kool-Aid? Well, who wants to drink Kool-Aid for that matter, but yeah, that's another story. Well, but why would this make a difference? Well, it turns out when you heat something up, they go faster. That's called an increase in kinetic energy. Motion creates collisions. So if you're going to make things move faster, they're going to collide harder, and they're going to break apart the ions more quickly. The hydration ion it will now be more effectively pulling the ions away from each other. So, increase the temperature would be a second way. A third way to get it dissolved is sometimes when you dump sugar in, you get these big clumps. And it's really hard to get the clumps to dissolve. And why is that? Well, because on the outside surface, you have only the areas that the water can attack. And there's a whole bunch inside that's available to be attacked, but it won't be attacked because it's being protected by the outside layer. So you're going to crush it. You're going to get the wooden spoon and start smashing it down. Why? Now the inside surface areas of all those crystals become available, and that crushing causes the collisions to occur as well, and that means you're going to be increasing the rate at which it's going to dissolve. So the bottom line, 3 ways to dissolve a solid in a solvent. Agitate the solution, increase the temperature of the solution, increase the surface area. That's what we call the crushing thing. So increase the surface. Now, we have a chart that is going to be used for the next part of this lab. So let's go ahead and get that up. So pause it right now, and we will continue on from that when you get that up. So this is the chart here. You got all kinds of lines and curves and everything going on here, but they tell you which substance is being dissolved. Now, the comparison here is the temperature at which you are going to dissolve this, and then over here is the rate of dissolving, which is measured in the amount of solute, the grams of solute per 100 grams of water. And these values right here are the grams of the solute. And as you see, the ionic compounds, the compounds with the metals in them, increase in temperature for the most part. The only exception is there's not even iron. There's one exception that always comes with these things. But now the ones that are going down, these are all non-metals. Yes, are better known as covalent compounds: sulfur dioxide, ammonia, and hydrogen chloride. Everything else is going up because they are ionic compounds. Okay? Now, so, I'm going to try and get this attached inside the lesson as well, the link, rather than get off this, because I know it's hard to do that. So I'm going to experiment a bit this weekend on that and see if I can't get that to work correctly. This will have a solubility chart of certain solids that I described to you. The first thing we're going to do, we're going to look at one of the compounds. That is KCl3, better known as potassium chloride. And we're going to look at how much will dissolve in water at 30 degrees. So we go to that chart. So here's potassium chlorate right here. Follow that until it hits 30 degrees. And it looks like it's just above the 10. So we can say it's 10 or 11 grams per 100 grams of water. The entire label has to be placed on that. So we would say, let's just say it was 11 grams. So we would write the answer as 11 grams per 100 grams of water. So based upon that idea, I want you to practice using the chart by finding these values at the temperatures I've described, and giving the answer all in grams per 100 grams of water. All right, have fun.